Okay, so what the idea is that this lesson is going to be all about breaking vectors down into components. Now, and then of course combining those components up to make a single vector. Now, I could have said it like that, but I didn't like using that language because in a lot of ways you guys won't be familiar with the word components and stuff like that. So I thought breaking and gluing vectors would be a good name for a title because that's what we're going to be doing. We're going to be taking vectors, we're going to be breaking them into smaller parts. We're going to take small little vectors and glue them together and see if we can make bigger vectors. And how does that work? We're going to rely on some of the things we've already learnt about vectors, and we're also going to expand it. At the very end, I'm going to give you guys some homework. The homework I'm going to give you guys, by the way, remember that the Stolen Ideas homework task is due on Wednesday. The homework I'm going to give you guys, I'm going to give you a week to do, is going to be motion 1. And so motion 1 will be due next week, and what I'll do is I'll put a thing on the Google Classroom so you guys can upload it, and I'll get to that in a sec. Before we do that, let's go backwards a couple of slides to see what we did last time. Last time what we were looking at was we were looking at the vector operations. We said, okay, can you add vectors? And guess what? You can add vectors. Vector addition means you can go from vector addition just means that we can go from A to B and from B to C, and that's the same as adding A to C. So you can add small vectors together. And then we did equivalent vectors. So if I've got A to D happens to be the same thing as, A to D happens to be the same thing as A to B to C, and so on and so forth. Now, after we did that, we spent a little bit of time talking about adding components, and that's exactly what we just did, in that if we have A plus B, you would just add up all the I components and all of the J components. This is very similar to what we just did. We did some examples of how you would go about adding these. We said A plus B. Let's grab a look at this one down the bottom. Hold on a sec. A plus BE, that's the same as saying going from A to B and from B to E. So therefore, the shortcut is A straight to E. So that is what happens when you add those two vectors together. We learned how to multiply vectors. So we said that okay, 2A's happens to be twice as long as vector A. It's like following vector A and then following it again. Because remember, a vector is just a length and a direction. So if you're saying walk 2 meters north and then walk 2 meters north again, then that's the same as saying 2A. Half A, by the way, is if you measure half of that. So if you've got a half A, then you're measuring half of this. And that would be the same as saying if A is walking 2 steps north, then half A would be walking 1 step north. And then we actually showed you guys that if you take 3B, it's like if B is walking to the right 3 and then up 4, then 2B is walking to the right 6 and up 8, because I've just doubled both of those numbers. And that's what we did just before when we wanted to calculate 2B. We just doubled both of those numbers. And that's what we just did as well in the attendance question, was a combination of this and adding vectors together. So it was actually a good practice for you guys. And we did an example here where we said DE happens to be the same as 2DC. Because if you look at DE, right, DE is all the way from the bottom up, which is the same as going halfway and then halfway again, which is why it's 2DC. Now, the only one that we didn't cover, and we're going to do this one today, right now, is we're going to talk about vector subtraction. So, because today what we're going to talk about is breaking and gluing vectors, but before we do that, we need to finish up the last lesson, which included vector subtraction. Now, vector subtraction, technically you can't subtract vectors. So what we can do is we can get around that by doing something like this. You can't subtract vectors, but what you can do is you can add negative vectors. So the negative of a vector is a vector with the same size, but it's in the opposite direction. So over on the right here, we've got some examples. Where is it? So here, we've got v and negative v. So v and negative v are in the opposite directions. So therefore, if I want to subtract v from something, I can just add the negative version. And so here's an interesting set of steps that we can do down the bottom. AB minus DB. Now you can't actually subtract vectors like this, right? But what we could do is we could add the negative vector. So what's that? Well, if you think about this, if we're subtracting DB, the negative of DB is BD. Why? Because BD is in the opposite direction of DB. If you've got D and then you've got B down here, the vector, the negative of vector DB is in the opposite direction. It's going to be a negative, and that negative is going to be BD. So if I want to write down DB, that's the same as saying, well, take the vector BD, but go backwards along them. That's why there's a negative. Just so happens that two negatives cancel out to make a positive, and that's how you get vector AD. So I can't subtract DB from AB, but what I can do is I can turn it into a negative. Now, I will say that if I'm dealing with stuff like 3i plus 2j, I don't need to worry about this. I can just subtract vectors like this pretty easily. But yeah, in a vector situation like this, you just got to remember it's in the opposite direction. And you guys are going to get a little bit of a chance to play around with that. But the cheat code that I think of is this. If you have a vector BC, then CB is going to be the negative of BC. That's kind of how the rule works. You kind of need to play around with this in real life to get a bit of an idea of how to do it. So I'm going to give you guys a chance at the end of this lesson to work on some of the questions. And I'm going to go through what those questions are later on. But for now, I'm going to skip the square challenge. This is a kind of neat little challenge. If you want to do this later on, you can. AB minus DA, and this is the situation here. The trick with this one is to remember that a negative of a negative makes a positive. So this becomes AB minus negative AD. And then that sort of starts to help you figure out how to solve this. But if you want to challenge, you can do this later on. But at the moment, we're just going to leave this here. We talked about this. So let's jump into today's lesson, breaking and gluing vectors. Now, I'm going to skip this bit because this is just a bit of a warm-up. We've already done a warm-up because we've done the attendance question, but this is the same sort of thing. This is the slide that I wanted to start on. What we're going to do is we're going to look at the two ways that we can talk about vectors and how we can go from one way of talking about vectors to a different way. I said all vectors are a size and a direction. So that's pretty much, when I say, oh, it's just a size and a direction, that's what this is here. A size and an angle, which that might be the direction. So it might be northeast or north 45 degrees east. If you've done bearings before in maths, this might be familiar to you. If you haven't, that's okay, but that's going to be how we can use an angle and a direction. The other one is ij components. Now, we've already talked about ij components. We've already got a bit of an understanding of them. But what we're going to be focusing on for this whole double period is this blue line and this green line. How can we go from one of these to the other? And then how do we go backwards? And actually, to try to help us out, I'm going to break this lesson into two sections. The first section is going to be just about this going from left to right. It's going to be just about how do we go from here to here? How do we go from angle and size to ij components? I'm going to use this blue line. And in fact, see how I've got a blue line at the top of this slide? All that's there for is to remind us that we're going from size to making ij components. You can think about this as breaking a vector into smaller, littler vectors, I vectors and j vectors. And the second part, this green line, that doesn't come until about halfway through the lesson, is how do we go from ij components back to a size? So that's going to be halfway through the lesson we do that. And that's going to be how do we go from here back to an angle and a size? And so by the end of it, we should be able to go both ways around. And then probably next week, I'm going to give you guys a homework sheet which is going to be practicing these skills. So let's try. Let's give this a go, starting about now. We've got about, looking at my watch, we've got about an hour and 10 minutes to do this, so let's go. Let's start off with component vectors. And so we're going to start off with what is a component vector. And this is a pencil here, so I'd like you to write this down. Any vector at all, can be represented as the sum of two other vectors, or more, but we're just going to see with two other vectors. Usually we represent a vector as components of a horizontal and a vertical vector. So if I take this vector here, it's going up and to the right, what we would normally do is we can break this down into two components. The components are a vertical component and a horizontal component. This actually has the name called resolving. What we do is we say we resolve a vector, which is the same as saying we break a vector down into its smaller components. And that's what we're going to start off with. See, we're going to break a vector into smaller up and down, left and right components. I'm going to give you guys a fraction of a second to copy this down, and then we're going to move on. Okay. So if any vector can be broken down into two other vectors, usually north and south, north and east, or horizontal and vertical, or I and j, how do we do this? How do we break a vector down into its smaller components? By the way, guys, I've just uploaded lesson 1 of this whole topic onto YouTube. So what I'm going to be doing is, over the next couple of days, is putting these lessons on YouTube. So if you do want to look at this later on, you can. So if we're going a bit too quickly, then you can check this up later on. Let's grab a look. And none of your faces will be on YouTube. That's one of the hardest parts about making these videos, is then editing them so I can remove all of the videos and stuff. So we're going to take this vector here, OP, and I'd like you to draw this little bit here. We're going to add a lot of details to this, but we're going to start off with just this thing here. We're going to start with vector OP. Vector OP has an x component, which we're going to call P of x, because it's in the x direction. It's an x component, and P of y, because it's a vertical component. So it's in the vertical direction. So just start off by getting this copied down, and then we're going to just go into some details. Okay. Now, to be honest with you, this is actually not very helpful to us because, you know, it's useful, but it's not super useful. These lines, by the way, are like if you had a shadow, if you had a light up here and you're casting a shadow downwards, that's like casting a shadow to make P of X. And if I had a light over here and I was casting it onto the Y, that's where I get P of Y. But it's a bit confusing because this is not how we normally would set up this problem. I think what would make life easier is if we did, by the way, this is the angle OP, and the angle, by the way, from P of X up to here. And this angle is what we would normally use to define the direction. You say, well, what is the direction from X? Normally you guys might be saying, but surely it's from north. And yeah, you're right. Normally we would say north something. But in this case, the angle is usually always from the horizontal. So OP is a position vector for point P. That's what it is. We're going to move this red line over to this side here. That actually makes this life a lot easier because now you can see we make a triangle. What type of triangle have we just made, ladies and gents? This is a question for you guys. A right angle triangle. Thank you very much. This is a right angle triangle. We've got an angle here, which we used to represent the length of this, and we've got the length of this vector. Remember, that's what we need for this side, a size and a direction. So like saying 22 kilometers northeast, that's a size and a direction. So if we've got OP, right, what happens if I have a problem here? What happens if I want to calculate one of those two components? How do I calculate the component of X? How do I calculate the component of Y? Someone want to give me a suggestion of what they think we might do to calculate components of X and Y? What do you think the next part's going to need? Pythagoras? No, it's not Pythagoras, Oliver. Good guess. Any other ideas? Trig? It is in fact trig. Let's grab a look and we'll see how. So we're going to start off by, oops. Let's work out the P of Y. Now the P of Y is this red line here. This is our vertical component, so that means it's our J component. Remember, I is horizontal, J is up and down, J for jump. Okay, so we're going to work out how can I take an angle and the size of this line and find out what P of Y is. Well, there's a couple of steps here. The first would be, okay, well, this happens to be, we want to know the opposite side of this line. So we're going to use sine. Sine theta, so the sine of the angle, right, is equal to the opposite side, which is this side here, which is opposite the angle, over the hypotenuse. The hypotenuse of the angle is this here. Now, we don't know what P of X is, so that's why we're not using tan. We can't use tan because we have no idea. Now, in this case, and of course, if I was doing this with my board, I would label this green side H, I would label this red side O, I would label this blue side A, but I don't have that here. And if I try to do that, if I try to do that, it kind of will look really weird. I can try my best. But yeah, it's not the greatest, is it? Okay, so we know that it's opposite over hypotenuse. In this case, our opposite side happens to be P of Y, which is actually pretty good. And we now know that our hypotenuse, which is this green line, is the size of P. It's how long this line here is. Okay, so that means that if I now replace, I can actually replace this with one cute little, well, not cute, but little addition here. Instead of saying size of P, I'm just going to put these bars down. You guys remember when we were talking about magnitude, these lines mean that we're just working out how long the vector is. We still haven't found a way to calculate py yet, but if I move this size of p over to this side, I get this. P of y equals the size of p times sine theta. And that is a great way to find out what is the vertical component of a vector by using sine. You have to know what this angle is, but it's a good way of working it out. Okay, I'm going to give you guys a fraction of a second to copy this down if you haven't done this already, but very, very quickly we're going to start working on p of x. Okay, so just get this copied down. I'm going to give you guys what, say a minute from now. Yeah, we'll go to that. I'm actually going to fill my drink bottle up. That's what I'm going to do. When I come back, we'll go to p of x. Okay, that's been about a minute, so it's time to move on to p of x. But guess what? P of x is very, very similar. P of x looks at the horizontal movement, the left or right movement, and it calculates the I component. Now, can I get a suggestion from chat? Which trigonometric identity do you think that we're going to use to find out P of x? And I've got two straight off, cos. Yep, it is cos. If we use sine because it's opposite of our hypotenuse, we're going to use cos because it is, wait for it, adjacent over hypotenuse. And if you watch, by the way, this side, these both are going to be very, very similar. Adjacent over hypotenuse. Adjacent in this size is P of x. Hypotenuse is the size of P. So this is great. This is easy, which means that the next step here is to say, well, therefore, cosine theta equals P of x over the size of P, or however long P is. And then we've got one last little bit here, which is to say that P of x equals the size of P times cosine theta. That will give you your I component. So now you've got your I component and your J component. And now that is the method that you need to calculate your IJ components. What you need to do is you need to know the length of the vector, you need to know sine and cosine and how to rearrange them too. So if you're not confident with your trigonometry, you might have to spend a little bit more time working on this to make sure that you know what you're doing. Okay, so next up, actually, I'll probably keep this up for just another 30 seconds longer. Are there any questions on this? Queries? Am I going too quickly? Maybe, maybe not. If I am, you gotta let me know. Okay, and then 5, 4, 3, 2, 1. Okay, next slide. Let's keep going. Let's do some examples. I've got 2 examples here before we jump into the next one. Okay, so this one here, I would like you to quickly jot this down into your books. Don't have to be precise, just close enough will do. just even if you just draw a line, you're at 6.750 degrees, that'll do. We're going to find the vertical component and the horizontal component of this vector. Okay. So roughly, how do we do this? Okay, I'm going to show you guys now. Here's my back to my leap of technology, going back to my phone to show you guys visually how to do it. Again, I apologize, but this is the only way that I have available to me. So let's do this. So if I push this over here, this is roughly what we've got going on. Yep. Some of you guys will probably have the slides open as well at the same time. If you do, great. So this is 6.7. And this down the angle here is 50 degrees. So now the first thing I'm going to do is I'm going to turn this into a triangle, a right angle triangle. I'm going to do that by dropping down this line here. I'm putting a right angle there. Okay, perfect. Good. Now let's just say I want to find P of X. I want to find this horizontal component first. This is P of X or whatever it is. You know, it doesn't matter what it is. The vector X. Yep. Can someone tell me which? Someone remind me which identity should I be using if I want to find P of X? Just remind me in chat. Which identity do I need for X? Is it sine, cos, or tan? Cos. Yeah, we're going to use cos. Let's do this together. Let's work it out. We've got the opposite side here, the adjacent side here, the hypotenuse. We want to know P of X, so we're going to use A. So therefore, we end up with cosine theta equals adjacent over hypotenuse. In this case, cosine theta, well, theta is 50 degrees. Cosine 50 degrees equals A, which is P of X, over H, which is 6.7. So then we end up with P of X equals 6.7 times cosine 50. Six 6.7 times cosine 50. 4.3. We're going to deal with stick stop there. 4.3. Cool. All right. What about when I want to calculate P of, and you guys should be copying this down as well into your where it says horizontal component. So now, how do I do the vertical one? What identity do you think I will use for the vertical line? So now how do I find this one? P of Y. Sine, yep, thank you, Evan. Ewan, sine. So Ewan, how do we do this? We go sine theta equals opposite over hypotenuse. Now, opposite side in this case happens to be P of y. Angle is 50 degrees. Sine 50 times, in this case, P of y, which is equals, sorry, P of y over hypotenuse, which is 6.7. P of y equals 6.7 times sine of 50 equals. I wonder if I can just go like this. Oh, look at that. Let's just delete cosine and put sine. Oh my god, so lazy, but the best. 5.12, 5.1. So we go with 5.1. So that means, by the way, we can actually rewrite P at this point. We can now rewrite P to be P equals, we'll go with, go with vector P equals 4.3i plus 5.1j. That's actually the vector that we've just calculated. 4.3i plus 5.1j. And that's broken down into two components, the horizontal component and the vertical component. Let's have a quick look at this. Because you can actually see on this, right? If we look at the vertical component, the horizontal component, how far across it is, it's 1, 2, 3, 4, and it's a little bit more than 4. So 4.3 makes sense. Let's look at the vertical component. 1, 2, 3, 4, 5, and a little bit more than 5 makes 5.1. That makes sense. So instead of going up at this angle, we could go across 4.3 and up 5.1. So that's how you do that one. We're going to do one more example really quickly. And when I say really quickly, I'm actually going to double time this next example. Because I'm going to go, so, but I wanted to show you guys one more at least, which is this one here. Now I like this one because it's a more of an application type question. We've got to always, and this is one of the things that my job that I really think is important, is to always come back and remember we're doing engineering maths. So what is the engineering here? Well, let's just say that you've got a pole that needs to be pulled down, a flagpole, and it needs to be pulled down into the ground, okay? If this flagpole isn't pulled down into the ground with enough force, then it's maybe it could slip and it could fall over. So what we might want to know is, well, how much is it getting pulled down into the ground by this guide wire? What is the vertical component of this pull? And you can actually calculate this. I'm going to give you guys a quick second to, actually, you know what, I'm just going to draw it. So if you guys want to follow along with me, instead, you guys can just follow along with me. And then instead of just trying to, oops. Here we go. Okay, so we've got our flagpole here. Now the flagpole happens to have a guiding wire, and that's what this wire is here. And that wire is having enough tension to pull down at 723 newtons. force happens to be one of our happens to be a vector quantity. So if it's pulling down, and it happens to be at an angle of 52.7. What that means is that if we want to do the vertical, if I then label this, by the way, opposite, adjacent, hypotenuse, if I want to know the horizontal component, that's adjacent and hypotenuse, that's going to be cosine theta equals adjacent over hypotenuse, which means that I've got cosine of 52.7 equals the A over 723, which means that our horizontal component is going to be cosine 52.7 times 723. Now I'm going through this one a bit faster than the other one because at this point now you guys have sort of seen all there is to it. You know, there's not really too much there. 438 newtons. 438 newtons. We're going to say left because that's where that's the direction that this is like left. Whereas the vertical force, we're going to skip some steps, is going to be O equals sine of 52.7 times 723. I've skipped these first two steps and just jumped to this one, which is going to be oops. 575 newtons. So that's the force downwards, right? That is this force here that is pulling this pole into the ground. The force that's pulling this pole into the ground is 575 newtons. You might find that, hey, you need more than 575 newtons. So you might need to add another guiding wire. Maybe safety restrictions say you have to have at least 1,000 newtons or something pulling your flagpole into the ground. Otherwise, it's not safe. So that's how that kind of question can be done. So now you've seen how to do it and two examples. So I'm pretty confident that I've covered that. So I'm going to jump ahead now to the next idea, which is, okay, well, how do we go back the other way? How do we go from two components like v of x and v of y? It doesn't matter if I'm saying p of x or v of x or m of x, it doesn't matter. How do I take two vector components and combine them together? Well, this is where we need Pythagoras. So in this case, given the horizontal and the vertical components, if I tell you the I and the j components, you know, or the x and the y components, you can use that to calculate the size. The size of a vector is the x component squared plus the y component squared, square rooted. That gives you the size. This is Pythagoras theorem. So if you're like looking at this being like, oh crap, I've got to learn a brand new equation. This is just v squared equals v of x squared plus v of y squared. The only difference is I've square rooted it so that I can make more, so I can just make it work. But that's only half the story. I need more than just the size. I also need the direction, right? So this gives you the magnitude. So how do I find the direction? The direction can be found by using inverse tan. Remember, tan is opposite over adjacent. So this angle here is the opposite over adjacent. So it's the v of y divided by the v of x. I'm going to give you guys a second to copy that down. And then we're going to give ourselves a bit of an example. We're going to give it a crack. We're going to see how we go. So we're pulling out, this is intense, this one, because then it uses both Pythagoras and trigonometry. Also, this -1 here, remember, means inverse. It will find the angle, not the missing sides. That's important for us because that's what we're looking for. I'm going to give you guys another, 30 seconds from now. And we're going to jump on. Unless someone needs more time, if someone needs more time and they want to write down in chat that you need a little bit longer to copy this slide down, and let me know. And the trick to knowing you need to copy this down is this pencil here. As I'm trying to go quickly because I would love to give you guys a chance to work on some of the questions, and I want to show you what questions I want you to work on. Yeah, of course I can show you how to do the investing in the calculator. That's going to be the whole point of the example, which I'm about to do right now. Hold on. I need another piece of paper. Okay. Okay, so we're going to do this example here. I'm actually going to, it's a pretty standard example, I know, but you know, like, it doesn't matter. I'm going to do it anyway. I'm going to, give me a second, so I'm going to plot this. I'm going to go back to my second camera, and then we're going to do it. Okay, so second camera away, here we go. So we've got a vector. We're going to call this vector, we can call it whatever we want. Let's call it S because, you know, why not? Vector S. I'm actually going to signify, because it's just one letter. Usually when you just got one letter, you just do a little tilde under the bottom of it. So vector S happens to be, in this case, 3i plus 4j. Now remember, I is a horizontal component. So that's like saying, oh, we've got a vector along here, it's like 3i or 3, and we've got a vertical one that's like 4. What we want to know is what is this and what is this distance here, and then what is this angle here. I'm going to do both of those now. So first things first, the magnitude of this vector, in this case, the size of S is equal to the square root of 3 squared plus 4 squared. Now I picked this for the obvious reason that the square root of 3 squared is 9 plus 40 is 16 equals 25 equals 5. So there is this, that's the size of this vector. This vector is 5 long. Even though each component is less than 5, the whole thing is 5 long. And if you wanted to put this straight in your calculator, you could just go, oh, well, I don't know what 3 squared is, so you would just go, right, square root of 3 squared plus 4 squared, 5. Perfect. Done. Easy. Okay. So there is our size, but we also need a direction. The direction, which is this one here, is going to be inverse tan of the inverse tan of, in this case, I'm just going to go s of x over s of y. So the vertical, oops, crap, I stuffed that up. I'm sorry. Inverse tan of the opposite over the adjacent, which is equal to inverse tan, in this case, of the vertical over the horizontal. Now, this is actually, by the way, this is why I always advise you guys to draw a picture, because sometimes it helps you understand what's going on. If I hadn't have drawn a picture, I would have done this and I would have made a mistake. In this case, s of y, the up and down, is 4. And the left and right is 3. So 4 over 3, how do you do that? Well, let's pop open a calculator here. I'm going to go my calculator, shift tan. So that's second tan. Now, if you want to be like, I know that you guys all like being fancy and stuff, so I'll do the fancy. No, actually, I can't. Can I do the fancy? No, I can't. You know what stuff? I'm not going to do the fancy. I'm just going to write 4 divided by 3. Why? Because that's what this line means. 4 divided by 3. If you want to, you could maybe use this button here, which is this fraction symbol. But for some reason, my calculator doesn't do that nice box thing where you get the boxes like that. If yours does, then great. But if I do this, I get 53 degrees. So that means this vector, vector S, is also the same as S is 5 units at 53 degrees from the horizontal. You don't always have to write that down, but if it says what is the S, what is S in a size and an angle, then that is what you should put down. And if it gives you a question where it asks you to do it. There was a question, there is a couple of things popping up in chat. So would you lose marks if you don't show the working out, for example, during the test? You won't, let me see. Okay, firstly, the part that I struggle with when students lose marks is this. They make, see how I made, if you made this mistake here that I just did, right? You would have got an answer of 27 degrees. If you wrote down 27 degrees, you get 0 marks. Okay, because it's completely wrong. If you write down this and you write down 27 degrees, you get 1 mark. Because even though you got the wrong answer, at least you showed me the right working. So here's the thing, and this is the same thing. I say this to my year 11s, I say this to my year 7s, I say this to my year 9s, I'm saying it to you guys. In my opinion, do you have to show working out? The honest answer is no. As long as you're 100% sure that you got the right answer, which even I am never 100% sure. So if you are not 100% sure that you're going to get the right answer, then you should probably show your working out. Okay? You should show your working out. There are situations that I am more, if I give you guys a question that's like, oh, what's 2 plus, if I, oops, sorry. Oh, my phone's falling. So if I give you a question, it's like, oh, what's 2 plus 3, okay? And you wrote down, oh, the answer's 5. Yeah, of course, good. You know, no working out needed. You're not going to go 2 plus 3, okay? I have to show working out. So 1, 2, plus 1, 2, 3, and then therefore 2 plus 3 equals 5. I don't care about that because I'm 100% sure that 2 plus 3 equals 5. I'm not 100% sure that the inverse tan of opposite over adjacent is 53 degrees. And because I'm not 100% sure, I'm going to show the working out. You won't lose marks as long as it's 100% correct. And that's sort of true for all subjects. A lot of teachers will, I'm going to try and be real with you guys. A lot of teachers will tell you, you have to show working out. And sometimes there are some questions which say you have to show working out to get full marks. In my opinion, you don't have to show working out to get full marks. Even when I mark general maths tests, I'm like, oh, you don't have to show full marks. But if you make a mistake and you haven't shown working out, you get 0. You make a mistake and you have shown working out, you could get half the marks. Sometimes you get actually 3. If it's a 4-mark question, you might get 3 out of 4 marks because you made one little mistake. Because if you make one little mistake and show no working out, you get 0. Hopefully that answers your question. Let's jump back to the page. So that now shows us the end here. This now shows us how to go from one to the other. If I want to go from an angle and a size to an IJ component, what do? Well, I use this logic here. If I want to find P of X, or the horizontal component, the I component, I go cosine times the length. If I want to find the vertical component, or the J component, I go the length times sine theta. Now, if I want to go from the IJ components back to an angle and a size, what I'm going to do is I'm going to use V of X squared plus V of Y squared and square root everything. Square the horizontal, square the vertical, and square root it. To find the angle, I need to go inverse tan of the vertical divided by the horizontal. That's right. I will do this briefly now, just because it's the last little thing. So I'm only going to spend 5 minutes on this. Now, I'm going to go back to my things. Just give me a sec. I briefly want to show you guys this. First things first, full disclosure, this is not on the test. Okay? However, some of you guys will be, after you finish this subject, you may end up doing maths method. So I actually wanted to take this opportunity and this is the very last thing I'm going to teach you guys with vectors. After this, we're moving on to more stuff with motion. But I'm going to take a little bit of time. I'm going to take 5 minutes, no more than 5 minutes, to show you guys something that will help you guys out if you decide to do methods, but also something that's really important for this topic too. One thing we've had a little bit of an issue with here is I've told you guys that the angle that we want is always from the horizontal, okay? And that's going to be true for all the questions that I give you. But there is a little bit of a catch here. What if I had 95 degrees? Well, that's going to be, if I measure 95 degrees from the horizontal, that's going to be so far around, it's actually going to be here. It's actually going to go the wrong way. 95 degrees is going to go this way here. And so we actually have a little bit of a problem here, because now what's going to happen is if we look here, right, the J component is positive, the I component is positive, whereas for this line here, the J component is still positive, but the I component, the left and right component, that is no longer positive. That is now a negative value because it goes to the left. We end up with this interesting problem here. So how do we get around this problem? I want to show you guys Oh, there's a problem in chat. Someone's like, what? Someone's already. This is unit circle. This is the unit circle. So what does this problem, how do I solve this problem about having a negative value? So what you can do, you can take this, right? Why have I drawn a circle here? Well, instead of, I'm going to draw this vector here, and I'm going to call this vector from this point to this point. We're going to call this angle here 30 degrees. This length here, instead of giving it some complicated, instead of giving it some complicated value, we're just going to call this length 1. Now, if I drew this vector here, I'm going to choose a very specific vector. This vector here that I've drawn happens to be, again, the same length, 1, but this time, this vector happens to be 150 degrees from the horizontal. Okay, now watch. Let's work out the ij components really quickly. The I component for this one is going to be cosine 30 times 1. That's going to be 0.86. Okay, cool. 0.86. Yep. Let's do the vertical component. The 0.86i. Let's do that. Let's do sine 30 times 1. Hey, 0.5. Okay, cool. So it's 0.5r. But let's now use the 150. Okay. What happens when I use the 150? What does that do to our problem? If I do cosine of 150, right? That's actually negative 0.86, which makes sense because it's actually negative. So that's going to be negative 0.86. It's actually the same distance. If I now look at the vertical line, this vertical line here, up and down, what's the vertical line up and down? It's a sine of 150. I'll put sine of a, look, it's the same value, 0.5j. But what's really important here is it's positive. That's exactly what we said would happen. This is 0.5j upwards is positive, 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 positive. Whereas here, positive, negative, positive, negative. But the interesting part is these numbers are the same. You might be saying, okay, whoops, sorry. Why is that significant? Okay. God damn it. You should have turned off my notifications. Jesus Christ. Okay, so why is this significant? Well, the reason that this is important is there is a link between 150 degrees and 30 degrees. Does anyone know what is the link between these two values? (180) equals minus 150 is 30 degrees. These two together make 180 degrees. In fact, this triangle here on the left, right, if I draw this over here, again, really quickly, this triangle on the left is the same as the triangle on the right. They are both 30-degree triangles. But we don't refer to this as a 30-degree triangle. We refer to this as a 150-degree triangle or 150-degree vector because 180 minus 30 gets 250. And that's why these are significant. This, ladies and gents, is something called the unit circle. Now, the unit circle is a topic that gets taught in I think it gets taught in year 11, but it might get taught in year 10 a little bit too, year 10 Actually, you probably already learned it in year 10, maybe. I don't know. But if you haven't, this is what the unit circle is. It's a way of, oops, it's a way of linking different parts of a circle. The reason why we care about it is later on, I'm going to give you a vector that looks like this. And when you put, you might not get a negative answer. You might be like, oh, you know, because this angle here is 20, if I say that angle there is 20 degrees, and you might get a positive answer, and you're like, to the vertical component. You're like, well, that's wrong. You're right, it is wrong. It should be down. The reason why that's wrong is because this 20-degree angle is actually the same as a 340-degree angle. And if you put that 340-degree angle in, you will get the right answer. But you don't need to know this for the test. You don't need to know this. I'm just showing you this so that you guys can get maybe an idea of what this is if you do this next year.